let's talk about ensemble methods. The motivation is that we want to take a simple, mediocre algorithm and transform it into a super predictor or a super classifier without requiring any fancy new algorithm or model to train. Now, typically, this is applied to what are known as weak base models. So base models are the models that collectively go in to make this super predictor. And they're weak in the sense that they need not have, amazing performance. All we ask of them is to have more than 50% performance. And we'll see that. We'll see why that is in a few slides. One example could be a decision stump. These are single node decision trees. Yesterday, we talked about decision trees having multiple layers, etc. You could have something that only has depth 1, and that's called a decision stump. Or they could be linear classifiers, which we'll talk about next lecture. So the definition of a classifier ensemble is a set of classifiers whose individual decisions are combined in some way. We'll go over 2 of those ways today. Classify new examples. The most famous examples of ensembles are known as bagging or bootstrap aggregation. This is parallel training of different classifiers on different training sets. And then we'll also talk about boosting. Instead of parallel training, now this is sequential training of different models, but now we're changing the data set itself to emphasize those examples where the classifiers have difficulty to do classification. There's also mixtures of experts, which is a bit more complex and we won't have time to talk about today. To finish up this introduction, ensembling is also sometimes known as meta-learning. So how does this relate to bias and variance? Consider this, this figure here. So let's say that I have some underlying data distribution from which I have 3 different training sets. And the point is that if I somehow find a way to aggregate my line fit on these different training sets sampled from P population, then maybe I would get closer to the actual true function that exists. So we can show that ensembling methods enable us to do both variance reduction as well as bias reduction. In the variance reduction case, if the training data used to train the base classifiers are completely independent of one another, it always helps to average an ensemble because this reduces variance without affecting the bias. Intuitively, what this means is that it reduces our sensitivity to individual data points, and that means that it would reduce our variance. In the case of bias, it's probably even more straightforward, because if we start with really simple models, take just a linear line, then the average of a bunch of linear models will increase the capacity that we have overall in the collective ensemble classifier. And so the average of the models can reduce bias by increasing capacity and control the variance, and that would be the boosting approach. Let's try to build some numerical intuition for this. Why are ensembles more accurate than individual members? I've probably alluded to this a couple times. It comes down to the differences in training data that exists across these base models, because errors that occur on these base models would be different from one another, and they would be independent of one another. What does this mean? I'm going to ask you a question, and I want everyone to take a few moments to think about this. Let's say that I have n classifiers, and each of these classifiers has an error rate of epsilon. Let's say epsilon is 30%. So my base models, I have n base models, and they're all 70% performant according to some measure of error. What is the probability that of these n models, more than half of them are wrong? Let's start with a simple case. Yes, Shima.
It's summation of the probability of the first classifier being wrong plus the second being wrong, and the being wrong means 0.7. And
so being wrong means 0.3, yes?
Oh, being wrong means, yes, 0.3. And the picking the first classifier, it means 1/n.
Okay.
And multiplied by 0.3 and something plus, yes.
So 1/n sum from I to n of probability of being wrong, which is 0.3. Is that what you're saying?
Being wrong, conditioned on the I model. I don't know. Yeah.
So how would I write? In this case, this would be these two cross out, and that would just be 0.3.
Oh, yes. Yes. Okay. Yes.
So let's take it step by step. Let's first ask yes, Pars.
Oh no, please continue, please.
No, I want to hear your thoughts, Pars.
Oh, okay. Now I think this would be like a maybe binomial distribution, correct? So because
Okay.
like either it's wrong or right. We don't know like the distribution. We assume that it's just 30%, right?
Okay.
Or if it's 30% of them are right, 30% of them or 70% of them are wrong, and then we would just like apply the summation of like n over 2 plus 1 of them being right all the way to n of them being right.
Mhm.
Or sorry, n of them being wrong, and then we add those up together, and then we would get our answer. But I'm not sure. Like there might be easier way to do it. I'm not sure.
Okay. Any other thoughts?
Yeah.
Okay, I think let's go with Parsa's idea, step by step. And let's start with the easy question. What is okay? The slides are not showing again. There we go. So what is the probability that one classifier is wrong? This is just a Bernoulli trial. We have a classifier. We know that P is equal to 30% of it being incorrect. We have an independent error rate of epsilon is equal to 0.3. So the probability that one classifier is wrong is just 0.3, independent of the rest. Yes? No? Nods? Excellent. So what is then the probability that K classifiers are wrong? As Parsa was saying, a binomial distribution is a distribution of having among n independent Bernoulli trials, how many of them are satisfied. And so we have a binomial distribution PMF, which can be written as P of n with each of them having success rate or failure rate epsilon, and we want K of them to be satisfied. Or the probability that number of errors is equal to K is n choose K. We want among n classifiers to choose K of them. K of them are going to fail, and the remainder are going to succeed. Someone who's nodding, help me explain this. Sahu, can you help me explain this?
I mean, if you can take as a binomial distribution, right? I mean, if K classifiers are wrong, so 1 minus K classifiers are at the same point of right. So, probability of something is like NCK and something to the power K, and then the component of this to the power n minus K.
Right. So this is combinatorics, basically, that maybe many of you have already studied. It's basically saying I have n independent objects. Each of them could fail, again, independently of one another. Remember, it says at the top, they're independent of one another, and they're also diverse, the assumption I'm making. And if that is the case, then I just have to choose K of them among all the n classifiers for them to fail. And I could choose, for instance, the first and the second, or the first and the 15th, or the second and the 27th, whatever. Any combination of selection of them times the probability of them failing. So on your own time, if it's not clear, please do review Bernoulli trials and binomial distributions, and it should become more clear. Now, the final step is to say, well, this is just a probability that K of the classifiers is wrong, but the initial question was, what is the probability that K over larger than n over 2? Basically, the majority of them are wrong, and that should be straightforward. We just sum over, we add the summation over the same distribution, right? So this is the probability that if I have n weak classifiers with independent error rates of epsilon, what is the probability that if I take the majority will also be wrong? That's what I'm trying to figure out. So let's add numbers to this. Let's say I have one model. I have one model with error rate 25%. What is the probability that the majority of models is wrong? Okay, this should be obvious, right? It's just 25%. One model in the whole ensemble. Let's say I have 5 models. Again, each of them with independent error rate. They could be the same error rate, but they're independent of one another. Independent error rate, epsilon 25%. Now, what is the probability that the majority is wrong? Let's take a few minutes to write this down, each of us. So what do I write for the first one then? We have 5 models. We're going to choose 3. We're going to say that those 3 are going to make an error, and the remaining 2 are not going to make an error. Can someone put this in a calculator and give me the number? 5 choose 3 is 10, by the way. Yes, Safida.
So I think it's 0.08.
0.087,
Mhm.
something like that. Yes? Others got this number as well? Okay. Anyone have the answer for the second one? That would be 0.15. And this third one is 0.001. So what's the point of this exercise? What's the takeaway? Yes, Shima.
Increasing the number of error is of low probability.
Okay, so for a fixed size ensemble, in this case 5, it's becoming increasingly more unlikely for all of them to be incorrect. Right. And interestingly, if you sum up these numbers, you get something that's relatively small. What is this? In this case, 1573. What is that? 103. You sum them up. That's 10%. Our initial models each had 25% error rate. And now with only 5 models, all of which had 25% error rate, if I take just majority voting, very simple, straightforward, I get something like a 10% error rate. So I've reduced my error rate by 60% already. So yes, the takeaway is that even with 5 weak models, only 75% accurate, then already the likelihood of the majority being wrong is very small. Good. If you want to practice more at home, you can do this, but summing up from 0 to 5. Now, let's see this maybe at scale. So now I'm considering another example where my base classifiers are 70% accurate. They have an error rate of 0.3. And I have, in this case, an ensemble of 21 classifiers. For the majority of 21 classifiers to be wrong, I need 11 of them to be incorrect. Yes? So if I zoom into this figure, 11 is right here. That's all the probability there is of the majority of 11 classifiers being wrong. And that's very small. That's 2%. And you can continue on, and you can say again, the model is 0.3 with 11 classifiers, or 21 classifiers, or 121 classifiers. The error just becomes completely negligible. Not just even for models that have 70% performance, but let's say, remember the weak model, I said the only condition is that the weak models should have above 50% accuracy. In this case, the second case, they have 51% accuracy. So ridiculous. If you increase the number of samples that you have in your ensemble, even a majority vote will also already reduce the error for you by a lot. Yes? No? Maybe? Yes, Jim.
What if all the models have high accuracy?
What would happen if all the models have high accuracy? What do we think? Guru.
In that case, we wouldn't require to do all this, right? I mean, we don't even need an ensemble. If the model is good, then...
Right. If you already have a strong model, you already have a strong model. But if it's like, let's say 80%, then it's similar between the comparison between these two cases, right? Here we need like 121 for us to be confident. Here we might need 10,000. But of course, the base models are just ridiculous. They're 51% accurate. Like a random throw. Shima, yes.
I mean, that's using 5 models of 80% accuracy can be achieved above 90% accuracy by
Perhaps. In this example, we had not 80%, but we had 75% accuracy. With 5 models already, we got close to 90%. So it's really just about plugging the numbers in. But I guess besides the actual digit values of performance, The point is that as long as you have weak classifiers, where the weak classifiers are above 50%, not inclusive of 50, but above 50% accurate, then the average of them are going to perform better, just by straightforward math. Now, these examples are a bit contrived because we're assuming that all of them are exactly the same error rate. Of course, in practice, that won't be the case, but that's fine. The math on average still works out, that as long as your weak classifiers are all better than random chance, in the case of binary, that means better than 50%, then the average of them will just perform better. Okay, so if you don't believe me that ensembles are important, there was something called a Netflix prize a few years ago. This was an open competition for the best collaborative filtering algorithm, and they wanted to predict, movie ratings and films for different users. And the prize winner, I think this was like $1 million check or something. Yes, it's $1 million check. So the prize winners, Belcore, used an ensemble of 107 different models, and they're quoted to say, our experience is that most efforts should be concentrated in deriving substantially different approaches, i.e. in this case, different base models, so they have different errors, they have variance reduction and bias reduction, etc., rather than refining one technique, rather than making a very powerful just one neural network. Maybe it's good to have the diversity in the errors and then average over them. We strongly believe that the success of an ensemble approach depends on its ability of its various predictors to expose different complementary aspects of the data. And experience shows that this is very different than optimizing the accuracy of each individual predictor. Yes? We're all sold on ensembling methods then? Good. Yes, Sapide.
So when we use ensemble methods, so we need more data, right?
That's an excellent question. When we use ensemble methods, we need more data. The answer is, it might seem like it, but actually we don't. We'll talk about bagging next, which is exactly how to use the same data set, but in different ways to create these different base models.
Thanks.
And to give you just a preview, if I have a data set with some number of samples and I'm only trying to optimize one model, then yes, of course, more data is helpful. But remember here, again, the point is not to get the best weak models. It's just to get a number of diverse weak models. So it's okay if we take a subset of those data set in different ways. Mujtaba.
When we increase the number of models, we reduce the error. But we also increasing the computation. So it is the trade-off between error and computation.
Absolutely. You're absolutely right. And this is one of the many trade-offs that you as machine learning designers will have to think about. Ensembles they might mean that you have a whole set of different models and you have to run all of them and do inference on all of them except for, instead of just doing one model. But at the same time, those models might be simpler. They might be decision stumps, for instance, right? And so it's not always straightforward as to whether it is more computationally expensive. But yes, if you have a large ensemble, then you're going to have to run a large set of models. Make sense? These are great questions, by the way. Any other questions?
Sorry, just to get it clear, when you say weak classifier, you also say like more than 50%. Let's say there are some classifiers in the ensemble model which are 49% correctly, accurately predicting results. How would that vary our results?
That's a very interesting question. So I'm going to maybe pull this question out of the context of ensembles and frame it a different way. Let's say I have a binary classifier, as Manavjit is saying. It predicts two different classes, right? A or B. And this has 49%, or I'm going to make it even more extreme. This has 40% performance accuracy. Again, it's a binary classifier, has 40% performance. Is this a useful model?
It's converse of a useful model.
It's a converse of a useful model. Okay. Should we just get rid of it and move on? Or is this a useful, can we do anything with it? And I'm gonna emphasize again with a hint that this is a binary classifier. That means the output is A or B. And it's 40% accurate. And it really only has two options as output. Yes, Shim.
Actually, it has 60% accuracy. Because
But I said 40%. How does it have 60% accuracy?
Because 40% means that
Manavjit got it.
predicts one class in 40 times, 40% of the time incorrectly, it means that we can use 1 minus the result of this classifier, and it will
Right.
be.
So a 40% accurate binary classifier is actually a 60% accurate binary. You just have to reverse the outputs.
Yeah.
Right? Is that satisfying or no? That was just too silly of an answer, Manavjit.
I mean, like, it's only for binary classifier in that sense, right?
Okay.
If
Yes,
we're
it's only for
talking
binary classifiers. Yeah, so in the case of, let's say you're classifying digits and you have 10 classes, you want to be above 10%. You don't want 9.9% because you can't flip it. Absolutely correct.
Yeah. Well, I get the idea, yes.
Okay, good. For binary classifiers, yes, almost all binary classifiers could be useful in an ensemble.
Yeah.
Okay, that's a great question.